I'm going to review for you the synthesis of nitriles because we're going to use them today. And then we also need to think about ring strains. So this is our 2301 topic. You learned about six-membered rings and chair configurations, oftentimes being the most stable configuration. And then when you have five-membered rings, you have different configurations versus 4 versus 3. There's a lot of strain associated with bonds in small ring sizes. So yes, please review that. That will become quite relevant. All right, we're going to learn about carboxylic acid synthesis. As I said, chapter 20 is all about carboxylic acid derivatives. So we kind of need to learn how to make carboxylic acids. I now see that my computer auto-corrected lactones to lactose. Okay, so thanks, Siri. And we'll look at some decarboxylation as well. So that's one of my favorite mechanisms to teach because we use it a lot. All right, let's jump into our learning objectives then. All right. So learning objective 19I is going to be about 2Ps. So we don't need to know the mechanism of this. This is a 2Ps of formation of carboxylic acids, right? Those are kind of front and center this chapter. And this is from nitriles. And if you're following along in the book, this is in 19.12. All right, so we learned a little bit about nitriles. We also call this functional group a cyano group. So let's go ahead, and this is a review of a 2301 or earlier 2302 topic. So before we get into our new learning objective, let's go ahead and review how we actually made the compounds that we're going to do hydrolysis on to turn them into carboxylic acids. All right, so we took alkyl halides, where of course X equals chloro, bromo, or iodo. Generally, when we see X, that's what it means. And we took these as our electrophiles in the reaction. And then we added in a nucleophilic source of cyanide. So in this case, we could add something like sodium cyanide. All right, and this was going to be our nucleophile in the reaction. All right, so we have this anion with a lone pair of electrons in our carbon for our cyano. So cyano, I'll draw it out for you. The functional groups look like this. So even though that's what the functional group looks like when we draw it out, we see a lone pair on nitrogen and we see a lone pair on carbon, but we see the negative charge on carbon. And so that's going to be our nucleophilic site here. So I don't want you to get confused, even though we have two lone pairs of nitrogen. The electron density resides with that anion on the cyanide. And so what you learned previously is this looks like a pretty great candidate for an SN2 reaction, right? We have an anionic nucleophile, a strong nucleophile. We have a good leaving group. And so what we learned was we could go ahead and add a cyanide to this, all right? Our byproducts are just going to be sodium and X minus. All right, so we use the cyanide nucleophile, but the functional group, when it's on a molecule, we call this a nitrile. All right, or a cyano group. Some functional groups, we found this with thioethers and sulfides, where different communities call them different names. All right. We also learned another way to make cyano groups and incorporate them into various different molecules by taking a different looking electrophile, an aldehyde or a ketone. And then we add it into our reaction. This is a two-step reaction. You'll recall we added sodium cyanide. We did learn the mechanism for this one, followed by water quench, or sorry, acid quench. And we made cyanohydrins. right? So these are molecules that we learned to make. And at the time, we didn't really see a purpose for them, for that cyanohydrin formation. This was the mechanism on the exam that we just had. But now we're going to actually do something with that nitrile group, all right? So that's why this is called an alpha hydroxy, where we have that alpha position has a hydroxy there. Okay, so that's what we learned previously. So now we know how to make nitrile containing compounds. And so now our learning objective is really what we can do with these different compounds, how we can convert these into a different format, all right? So this is really when the learning objective 19I comes in. We just had the 2 P's. So let's take our cyano group here. What I want you to know is, note is that we're going to make this product here. That is going to be a carboxylic acid. I think quite often people really want to call this an oxidation, all right? This is not an oxidation. The oxidation state of this carbon is bound to 3 heteroatoms. In this case, it's a nitrogen. And in this case, this carbon is also bound to 3 heteroatoms, has 3 bonds to heteroatoms, right? So 3 bonds to a heteroatom, even though that's nitrogen, 3 bonds to a heteroatom. Heteroatom means just non-carbon. And we see this is not an oxidation reaction, all right? This is just something called a hydrolysis. So we've added water, essentially. All right, so how do we do this? We use H2SO4, a little bit of water. We do need to add heat to this reaction as well. This is not, cyano groups are relatively stable, so we need to kind of cook it in a lot of acid, all right? So of course, it's always helpful to us to understand what our byproducts are. So we can see in our product here, we've added in oxygens, and those are coming from our water. And we have some protons, those are coming from our acid. We're missing a nitrogen. So at the end of the day, our nitrogen becomes NH4 plus ammonium, and our acid lost a proton, so we have a sulfate counterion. All right. So for me, at least, it's always really helpful to see where all of our atoms went. So of course, we have kept our carbon and we've lost our nitrogen. We see we keep our carbon and our nitrogen there. All right. So this is a hydrolysis reaction, not an oxidation. Right? I'm emphasizing this because on the exam, we often have reactions in which we take an alcohol and go to a carboxylic acid, or an alcohol and we go to an aldehyde or a ketone, or vice versa. And people often want to use the acid for those reactions, but acid is not an oxidant. So if we're going to see that happen, I don't want you to get confused, because this is not an oxidation reaction, so we can use acid for it. All right, let's see what we have when we have our alpha hydroxy group. The same thing is going to happen, same set of reagents. We're just going to make a different functional group at the end of the day. All right, we can add in our H2SO4, our water, and we can heat this up. And we're just going to have an additional OH. It hasn't done anything in this reaction, but we're going to see that we're going to make a special type of carboxylic acid, and this is called an alpha hydroxy carboxylic acid. All right, I'm just showing you this example here because we can have other functional groups in our molecule that are not going to get touched. Our alcohol is not going to get touched. It's not going to eliminate out under these conditions. We don't really know what R is, but the conditions are not ideal for that. We see that we still remain with our carboxylic acid. All right. So an alpha hydroxy carboxylic acid, or just a carboxylic acid from nitrile hydrolysis. All right, so as I said, we're going to move into a chapter with carboxylic acid. So it's a great idea to get this chemistry down. So I'm going to give you like maybe a little bit of a yes-no situation here. So this is going to be tips for carboxylic acid synthesis. Right, we've learned a lot of different ways to make carboxylic acid. So how do we know which way to do it, right? So we saw this kind of some of these choices in the lecture last time. Well, you know, do we have a benzylic CH? Do we have an alcohol with 2 alpha protons? Do we have an aldehyde? Do we have a lot of different choices? Can we add CO2? Here's the example where we can add a cyanide to an electrophile. So the question you can ask yourself is, can the synthesis work by adding a carbon? All right. If the answer to that question is no, you're not going to add a carbon here. You can use oxidation chemistry. All right, so in this case, our starting materials could be aldehydes. Can't start with a ketone. We don't have enough CHs on it, but we can have an aldehyde, a primary alcohol, a benzylic CH bond. Right, there's a number of different things that we can start with. All right, what if our answer to this question of, do you have to add a carbon, is going to be yes. And we can think about doing things like using an organometallic plus CO2, right? That's going to give us our carboxylic acid. We're going to add in that carbon here. All right. Or if the answer is yes, we can add a cyano group. Then do hydrolysis. All right, so counting carbons always comes into play, and especially when we're thinking about carboxylic acid synthesis, all right? So what I want you to always do on an exam or on the homework is count your carbons. Where are we getting this number of carbons from? Can we just oxidize a functional group, or do we need to add in a cyano group and then hydrolyze it, or use an organometallic? All right, we're going to revisit a reaction that we've actually already seen before, and we're going to form some esters from carboxylic acid. So this is the Fischer esterification, but previously we did not have a mechanism for this reaction. We just taught you the 2 P's of this to make an ester. So our next learning objective is going to kind of go back, and now we have the tools, because we understand the mechanisms from this chapter, to actually see how we're going to form esters. All right, so this is learning objective 19J. This is the 4 P's. So yes, there's a mechanism. So for the formation of esters from carboxylic acids, and alcohols. All right, continued. We'd see this before. Okay, we've seen the 2 P's of this. And the mechanism, so now with P3 and P4, you can find this in chapter 19.14. All right, so you're going to recognize this reaction where we have a carboxylic acid. Now we'll know a lot of ways to make that. This is going to be our electrophile in the reaction. We'll talk about why that is. Now, our other component in our reaction, you'll recall, was our nucleophile, and that was our alcohol. You'll recall we've talked a lot about Fischer esterification and ways to drive this reaction forward. So this is an acid catalyzed reaction. So we need an H plus source. We can use a lot of types of acids here. One good example could be tosic acid, but we can use a lot of different acids, and we need to heat this reaction up. And our Fischer esterification said that what we got at the end of the day was an ester. And we have water. One of the oxygen from our water is actually coming from our carboxylic acid. All right, we talked a lot of ways to drive this reaction forward. We talked about adding in more nucleophile, maybe running the reaction in an alcoholic solvent. We talked about maybe adding more of our electrophile. We also talked a lot about driving the reaction forward by removing water, right? This is where our actual piece of lab equipment, the Dean Stark trap, comes into play, so that we can sequester water in this reaction and drive it forward. All right, so we've talked extensively about this reaction, but we didn't quite have the tools yet to learn the mechanism. So let's think about how this mechanism, now that we understand a lot more chemistry and a lot more mechanistic tools, let's think about this mechanism. All right, what should we actually observe here? Well, something we should see is we have a strong acid. So if we have a strong acid, we're probably going to protonate something. All right, we have two choices to protonate. We have our carboxylic acid we could protonate. We see we have lone pairs, for example, on this carbonyl carbon, and the two lone pairs on the oxygen of the OH group. We also have lone pairs of electrons on our OH group, our nucleophile. But when we think about this, if our nucleophile gets protonated, it's no longer nucleophilic. So that really helps us to narrow down the fact that we're going to make a stronger electrophile by we're going to protonate our electrophile. So let's add that. Probably protonate electrophile. All right, let's think about other things here. So the carbon we're reacting with here, that carbon is CsP2 hybridized carbon. So this is not an SN2 reaction, right? That's kind of the first, one of the first mechanisms you ever learned. We see SN2 come up over and over and over again. But we don't have a good leaving group and an alkyl halide, and we don't have a CsP3 hybridized carbon, right? We have a CsP2 hybridized carbon. But we see that the carbonyl carbon, right? So here's our carbonyl carbon right here. So we see a carbonyl carbon in the aldehyde, we see it in a ketone, we see a C double bond O in many different functional groups, including this one. And so the carbonyl carbon is likely our electrophilic site. We've seen electrophiles attack there all semester. All right. We have a lot of options for that. Okay, so, this is the point in the semester. I really want you to start thinking through mechanisms before we launch in to actually drawing them, all right? Because we can actually, believe it or not, I know people think, oh, mechanisms are a black box. I just need to memorize it. But it turns out we can just understand the reactivity, and we can kind of correlate it to things we've already seen in this class before, and that's going to really help us understand the mechanism without having to do any sort of memorization. All right, so we have P4. We're going to kind of consider the things that we just said. So we are going to have our electrophile. We're going to see some lone pairs on that oxygen. Seems like a pretty good candidate for protonation to make a stronger electrophile. So we can use other acids. In this one, I'll just use tosic acid as a model acid. All right, we contain that lone pair of electrons on our oxygen. That electron density attacks that HO bond. We break that HO bond and return those electrons to the oxygen of the tosylate. Okay, so what that leaves us with is a protonated, stronger electrophile. All right, so we have this H plus now. So we have a positive charge on our oxygen. We always are going to want to carry through our tosylate counterion. We're going to see that show up again. Okay, excuse me. So now we have the opportunity where we have a stronger electrophile. Now seems to be a pretty good time to bring in our nucleophile. All right, we've seen carbonyl carbons undergo attack. That seems like a pretty great next step. So we take the lone pair on our oxygen over our alcohol, and we're going to go ahead and attack that carbonyl carbon. Then we're going to break that CO double bond, return those electrons from the bond to our oxygen so it can have a lone pair. All right, so now we see we have a tetrahedral carbon. We have this no longer positively charged on our carbonyl group. Wait, right, we broke that bond there. And now we do have a positive charge on our oxygen that just underwent nucleophilic attack. So we'll give our tosylate counterion its due here where we have it negatively charged. All right, so this seems like a great candidate to neutralize this molecule here. So we can deprotonate that OH bond using our tosylate counterion and get back to a neutral species. All right, so that gives us this tetrahedral intermediate with 3 bonds to different oxygens on our carbon that's now neutralized. So this is a neutral molecule. We can go ahead and bring back our tosylate or our tosic acid. All right, so this is looking pretty familiar. This is pretty familiar to things like the intermediates and hydrate formation. Instead of a ketone or an aldehyde, we now just have a carboxylic acid, so we have an extra OH group. All right, when we look at our product, we need to lose a molecule of water. So we can think of a pretty great 2 candidates, actually. We could use either OH group. At this point, they're the same. So we can use either OH group as our leaving group that we're going to turn into water. We're going to go ahead and protonate that using the tosic acid. We'll break that OH bond to give those electrons back to our tosylate. So we're just setting ourselves up to be able to get to using water as a leaving group. As I said, you could use either of your OH groups. Doesn't really matter. All right, so now we have a protonated oxygen here. We have our tosylate counterion that's negatively charged. Our oxygen is positively charged. Of course, we had made our bond with our alcohol. All right, so we've seen this next step before as well, right? We've seen a lone pair assisting the leaving of water in many, many different types of mechanisms. So let's go ahead and see that this lone pair on our oxygen can come down and go ahead and cause our water to leave, all right? Because it's already protonated, we don't have some sort of anionic group leaving in acidic conditions, and we're very close to the end of this mechanism. So now that leaves, we haven't done anything with a proton on the oxygen that came down and assisted our leaving. So we now have this intermediate that is still protonated. I'll carry through our tosylate counterion that we had before, which I drawn in the wrong color. All right, so we've lost water in this reaction. So we see that that oxygen did in fact come from our oxygen of our carboxylic acid, right? And that's what we had seen in these byproducts before. We had seen that that oxygen had come from our carboxylic acid. So the only thing left to do is to go ahead and just neutralize this compound. So we can go ahead and take Lone pairs of electrons in our tosic acid deprotonate this OH bond, return those electrons to our oxygen, and then we get to our ester functional group. And that's the end of our mechanism. So we've seen this mechanism before, right? We've seen protonation. And we've seen addition of our nucleophile. And elimination. You're going to see this protonation, addition, elimination sequence of mechanisms all throughout chapter 20. We're going to see it over and over and over again. All right, so there's a special form of carboxylic acid and a reaction with an alcohol that I want to go over with you all. And that's an intramolecular reaction, all right? So this is an intermolecular reaction, a reaction between two molecules. But if we wanted to, we could actually have these two molecules tethered together and we would form a ring. So if we had these tethered together, these R and R1 were going to be bound to the same carbon. We could see that this mechanism would be the same even if it was an intramolecular reaction, all right? We would have just made a ring in this case, right? So the dashed lines are if intramolecular. So intra meaning within the same molecule. All right. So it turns out the next learning objective is going to be the intramolecular reaction. You need the 4 P's. We just learned P4 for that reaction as well. So this is P4 for Fischer esterification. If it's intermolecular, we don't have those tethered R groups. And I'll show you some examples of actual molecules. But it turns out it's sort of a 2-for-1. If you know this mechanism, it's the same for inter and intramolecular reactions. All right. So we have the learning objective 19K. And this is going to be the 4 P's for lactone formation. So lactones are just esters that are in a ring. So I'm going to put in parentheses after lactones, I'm going to put cyclic esters. All right, that's the name of that functional group. This is, of course, from carboxylic acids and alcohols. Right, so the exact same learning objective we had before. Before we had the formation of esters from carboxylic esters and alcohols. Now we just have the cyclic version, and it forms something, a special type of ester, a cyclic ester called a lactone. So this is an intramolecular reaction. Right, and so in 19.5 is where you can find this. All right, so let's convince ourselves that we actually already know how to do this, all right? So if we wanted to form a cyclic ester, we could say, what do we know about the formation of esters in general? So we can recall that if we wanted to form, we had a retrosynthesis for an ester like we just saw, we would go retrosynthetically, and we would say that we would start with a carboxylic acid and an alcohol. That's what we just learned. All right, so if you now want a cyclic ester, so we'll draw our cycle here. The dashed lines mean it can work for many different ring sizes. It's not just restricted to certain ring size or one ring size. Then all we would need to do is we would have our carboxylic acid and our alcohol in the same molecule. Sorry, that should be an H. All right, so we have a carboxylic acid both here or here. The other molecule we need is an alcohol. We have that here or here. All right. So I'm talking about this quite a bit because for some reason, intramolecular reactions are quite challenging for some people to see. All right. And I get that. Sometimes you don't recognize a molecule is going to react with itself. So that's why we're taking a little bit of time to really go through and convince ourselves it's actually the exact same reaction that we had before. All right. So let's use an example here. And let's say we have a carboxylic acid. And our carboxylic acid chain is going to look like this. And we're going to have an alcohol at the end. All right. So in this case, we know that we can number these positions, alpha, beta, gamma. Right? We learned naming for carbonyl compounds like aldehydes and ketones. Turns out the exact same that we have for carboxylic acids. That's still the alpha position. Right? Great. So now how many carbons do we have in the chain? Let's say number of carbons in our ring plus number of oxygens. Let's see what that number is. All right, so the number of carbons in our ring is going to be carbon 1. Our carbonyl carbon, when we take a look at this up here, it's going to be our 1. Then we're going to have 2, 3, 4 carbons in our ring. And we're going to need to count this alcohol, all right? Recall that we lose this OH of our carboxylic acid, so we're not counting that as part of our ring. And so we have this alcohol as part of our ring. So our product of this reaction is going to be a 5-membered lactone. So we have 1, 2, 3, 4 carbons. Now we have our alcohol. And we have a 5-membered ring. All right. So the number of carbons in the ring plus our alcohol oxygen is going to give us our 5-membered ring, right? You already know the conditions for this. You already know it's going to need acid, water, and a little bit of heat, right? It's the same conditions for our ester. So what do we call this type of lactone? This would be alpha, beta, gamma. So we'd call this the gamma lactone. Right, so we name it based on the number of carbons in the ring. All right, so this is a gamma lactone. We could continue down and we would call those reactions. Beta lactone would be really, really strained. That would be challenging to make, but you could have an epsilon lactone if you wanted it to be larger and things like that. All right, so you already know the 4 P's of this reaction, right? Because P4 is simply if we had this molecule in a ring. Okay, let's go ahead and do a chime in to make sure that we're really able to get the idea of this lactone formation and how many carbons and oxygens are going to make up our ring size. Okay, so here's our chime in question. We'd like to understand what is the product of this reaction when the following acid is heated with a strong acid like sulfuric acid. Let's see what we would get in this reaction. And as a bonus for yourself, you can name it as well, so that's not part of the chime in. See what you would think it would be. All right, so we have about 50 people answer. Let's go ahead and see what people are thinking. All right, yeah, awesome. So a lot of people think it's D. I like that answer choice. We'll draw it out on the board. I understand why people think it's B as the second choice. That's the correct number of carbons. It's just a different connectivity. It has a branching point there. All right. So it makes sense to me why B and C are answers. We just saw A as an answer, so it can be kind of confusing. All right, so looks like 70 people have answered. That's a lot. So as always, if there's chime-in question issues, just come up after. I'll close this question. All right, so let's go ahead and see this chime-in here. And see what we had. So we had this molecule, this carboxylic acid with an OH group attached to it. All right, so we have alpha, beta, gamma, delta. All right, so that means in our ring, we're going to have 1, 2, 3, 4, 5, 6-membered ring. All right. So when we heat this up with H2SO4, what we're going to get out at the end of the day, we now have established it's going to be a 6-membered ring. Right, and we can go back and we can say alpha, beta, gamma, delta. So this is a delta lactone. All right, so we're always counting the number of carbons, including the carbonyl carbon, as well as the oxygen, when we're trying to figure out the ring size. So I'm going to note here that gamma and delta lactones are very common. And this goes back to our ring strain rules, right? We talked about a 2301 topic was to be ring strain. Right, so this can be able to accommodate the size of our lactones. We see these all the time. Actually, lactones are used a lot to make polymers, and they open up these ring sizes, all right? But I will say that 4-membered lactones are too strained to make. Right, we can make them, but not through the synthesis. So for the purposes of this class, they're too strained to make. All right. We cannot accommodate the energy necessary for us to be able to actually form that ring. All right. So we just commonly see 5 and 6-membered lactones. All right. And that makes sense, right, with ring strain. Okay, we have one final learning objective in this chapter. So that the end of this chapter is a little bit of a grab bag of things. But we're going to learn one more reaction with a carboxylic acid functional group. I think this is a kind of a fun reaction. And actually, it's a good segue into the chemistry that we're doing in a few weeks. All right, this is learning objective 19L. And this is 4 Ps. So we're going to learn a mechanism, and this mechanism is not going to be like a mechanism we've seen before. So we're going to have to think through it a little bit. So this is the 4 Ps for decarboxylation. So we lose a carboxylate group of diacids or diketones, keto acids. So keto acids have a ketone and an acid in them. This is in chapter 19.16. All right, so we need a very specific type of diacid, so dicarboxylic acid. All right, so what does a dicarboxylic acid look like? It's gonna look like something like this. Our diacid here, all right? And something that we need at the alpha position, so we need some CH bonds to be there. So at least one, all right? We can do this with a reaction with only one CH bond if you had another substitution here. Okay, and the only thing we're going to do in this reaction is we're going to heat this up quite hot. This is 150 degrees Celsius. right? I'll say we don't often use reactions that are heated this high, but this is a really, really, really common reaction in synthesis. What you get out at the end is we're going to keep those hydrogens, but we're going to use one of them at one point. You're going to get out your carboxylic acid, and you're going to lose CO2, right? And this is a gas, so it evolves in the reaction. So we're going to undergo a decarboxylation reaction. So decarboxylation is loss of CO2. The loss of a carboxylate group. Right, decarboxylative chemistry is like really, really common. All right. Carboxylic acids are just really prevalent in nature. They're very prevalent because we live under oxidative conditions on Earth. We breathe a lot of oxygen in, and oxygen reacts with functional groups that ends up making a lot of things into carboxylic acid. So yes. Okay, so let's take a look at what we see in this reaction. So I made a statement about you need one CH bond. Actually, as I'm looking at this mechanism, I think you could have a disubstituted carbon there. It would just be a slower reaction, so you don't actually need those CH bonds. I'm just drawing them out so you can see where they end up in the product. Okay, so let's take a look at this mechanism. I'm going to suggestively actually draw our molecule in a different configuration, all right? So instead of drawing it with our carboxylic acid, with the OH in the plane of the board, I'm going to draw it like this, all right? So we're priming ourselves for what needs to happen in this reaction. So this is going to be a cascade reaction. It's not an equilibrium because we're going to lose a gas, so it's just a straightforward arrow. And the only thing we do in this reaction is a series of arrows. It's concerted. So concerted means all in one step. Right, multiple arrows, but everything happens at the same time. All right. So what we're going to do is we're going to deprotonate our carboxylic acid using a lone pair of electrons from our oxygen. Then we're going to break our hydrogen-oxygen bond, put those electrons to make a double bond between that carbon and oxygen, right? We're trying to get to CO2. We can't have 5 bonds to carbon, so what we need to do is break this CC bond, make a double bond between our other carbon-carbon bond. Again, we can't have 5 bonds to carbon, so we're going to at the same time break our CO bond, all right? So this all happens at the same time, but I like to think about it as being kicked off by that deprotonation, all right? So let's go through that again. We're going to take the lone pair of electrons on our oxygen. We're going to deprotonate that OH bond. We're going to break that OH bond, and we're going to go ahead and make a carbon-carbon double bond at this carbon. That would mean that carbon would have 5 bonds, so we have to break this carbon-carbon bond at the same time and place those electrons to form another carbon-carbon bond here. But if we formed another carbon-carbon bond here, this carbon would have a double or 5 bonds to it, so we need to break this CO double bond by putting the electrons back. All right, so it's a lot of series of arrows, and if we follow that series of arrows, what we end up with is our oxygen at the top that is protonated. We end up with a CC double bond here. We see our 2 H's, and then we end up with CO2. All right, that was quite the series of arrows, but we got there in the end, all right? This functional group here is we're going to be revisited by this functional group a lot. This is called an enol, okay? an alkene and an alcohol. And it's going to undergo a mechanism that I'm not going to worry about at this point. It's going to undergo something called tautomerization. We're going to talk about this so much in the future that I'm not going to worry about it at this point. But what it's going to do is essentially it's going to isomerize from the enol back to the carboxylic acid. All right. So one final thing to note, that this reaction, I said, doesn't just work on diacids, it works on ketoacids as well. So say this was a methyl group, a ketone, or a phenyl group. We could just see that this reaction works throughout. We just need one equivalent of a carboxylic acid to undergo decarboxylation, all right? All right, so that is what I have for you today.